Hello friends, I am Utsav Kumar. Welcome back to my channel. So today we are going to discuss 5G air interface protocol stack. So the figure here shows the simplest version of protocol stack for 5G air interface from the viewpoint of mobile. So this figure assumes the use of architectural option 2 in which the mobile is controlled by 5G core network, the next generation radio access network, and a master next generation node B alone. Most of the protocols have the same names and objectives as their 4G equivalent, but their low-level implementations are different. So in the user plane, the mobile exchanges packets with an external data network such as the internet. Those packets are created by applications in the mobile and the data network and are transported over the network using protocols such as TCP and IP. In the control plane, the mobile exchanges non-access stratum signaling messages with the core network using 5G MM and 5G SM protocols, and exchanges access stratum messages with the radio access network using the protocol for radio resource control, that is RRC. So the next four protocols form layer 2 of an OSI protocol stack, that is the STAP, PTCP, RLC and MAC layers. So STAP is new to 5G. STAP is mainly the service data adaptation protocol, and it maps the quality of service flows used by the 5G core network onto the data radio bearers used by the NGRAN. Now coming to PDCP, it is the packet data convergence protocol. It secures the air interface traffic and signaling messages and routes packets through the correct base station in case of dual connectivity. The RLC protocol, that is the radio link control protocol, segments any large data packets before transmission and handles the high level retransmissions. Now coming to the MAC protocol, which is medium access control protocol. It schedules transmission between the mobile and the base station and controls the low level operation of physical layer. The MAC protocol in the mobile and network can also communicate with each other by exchange of MAC control elements. Now coming to the physical layer. So most of the complexity is in the physical layer, which has three main parts. So the number one is the transport channel processor, then physical channel processor, and the last one is analog processor. So the transport channel processor handles the remaining error management tasks, including low level retransmission by means of hybrid automatic repeat request, that is the HARQ. Now coming to physical channel processor. So it handles the remaining data signal processing tasks, notably the OFDMA and multiple antenna processing. Finally, the analog processor. It converts the information to analog form and transmits it. The physical layer also handles several procedures for measurement and control. So inside the core network, the 5G MM and 5G SM protocols are respectively implemented in the access and the mobility management function, that is AMF, and the SMF. In RAN side, the STAP is in the GNB central unit's user plane, and the PDCP is split between its user and control plane. The RRC protocol lies mainly in the central unit's control plane, although the distributed unit can send and receive a small number of unciphered RRC signaling messages as well. The RLC, MAC, and physical layer protocols all lies in the distributed unit. So the information flows between different protocols are known as channels and signals. Data and signaling messages travel on RLC channel between the PDCP and RLC, logical channels between RLC and MAC, transport channels between MAC and physical layer, and physical data channels within the physical layer itself. Within the physical layer, the transport channel processor in the mobile and network communicate by exchanging uplink and downlink control information, which is delivered by means of physical control channels. Similarly, the two physical channel processors communicate by exchanging physical signals at a higher level. The diagram here also shows the locations in the protocol stack of QoS flows and radio bearers. Moreover, for each protocol layer, we have the technical specifications listed as well in the figure for further reading. Now coming to channels and signals. So 5G uses several different types of channel and signal which are distinguished by the information that they carry and by the ways in which the information is processed. So they are listed in the tables shown here. So the number one is logical channels. So you can see the broadcast control channel, paging control channel, common control channel, dedicated traffic channel, and the corresponding information carried by them and the direction of the information, whether it is in the DL direction or it is bidirectional. If it is listed here UL and DL both, then it is bidirectional. For example, the common control channel, it carries the signaling messages on SRB0 and its direction is both UL and DL. Similarly, transport channels, it has broadcast, paging, downlink, shared channel, random access channel, and uplink shared channel, and their corresponding information, that is master information block, paging message, downlink traffic and signaling, random access request, uplink traffic and signaling. So these SRP, DRP, master information or SIP, whatever is written here, we will make a separate video on those topics as well in detail. So going further, the next one is the physical channels and their information. In the next table, you can see the control information. The field is DCI and UCI. The name is downlink control information and uplink control information, and what are the information carried by them. So the one is downlink schedule commands, uplink schedule grants, slot format indicator, preemption indication, power uplink power control command, uplink sounding requests. So these are basically the information carried in the DCI and UCI information control. Similarly, in the physical signals, which are PSS, SSS. So PSS and SSS are mainly for the mainly the synchronizing signals, which is used for the during the cell acquisition time. Then CSIRS, SRS, DMRS, PTRS. So each of these signals are needs to be discussed more in detail, and we will have a separate video again on these topics. So here mainly we are discussing very briefly on each and every channels and the signals. So the previous tables were mainly for the channels, and now this is the signal which mainly are carried by them. And going forward, now let's talk about the information flows. So here in the uplink information flows and downlink information flows, it basically shows the information carried by the channels and signals in 5G and the relationship between them for of the uplink and downlink respectively. So the arrows drawn from the viewpoint of the base station so that uplink and downlink channels have arrows pointing upward and downward. The 5G air interface delivers most of the mobile traffic and signaling on three bidirectional logical channels. The DTCH carries user plane traffic for single mobile, while the DCCH carries most of the control plane signaling. So all these channels we discussed in the previous slides. So this is now the information flow. Now coming to the common control channel, it carries signaling message on SRP0 for a mobile that is moving from RRC idle or RRC inactive into RRC connected. Those channels are transported by the downlink shared channel, that is the DLSCH, and physical downlink shared channel, that is PDSCH. In the downlink, and by the shared channel, uplink shared channel, sorry, correction here, that is the ULSCH, and physical uplink shared channel, that is PUSCH in the uplink. So a base station can send RRC signaling message known as system information to all the mobiles in the cell, which describes how the cell is configured. So at the highest level, that information is divided into two unequal parts. A base station can transmit a master information block, that is MEB, which contains a few important parameters that the mobile needs to acquire a cell, and is delivered on a broadcast control channel. Now the broadcast channel and physical broadcast channel, it also transmits several system information blocks which are numbered from SIB1 to SIB9. So they are delivered first on the broadcast channel in the same way as the MEB, and then on the DL-SCH and PD-SCH in the same way as the rest of the downlink signaling. Now a base station can also compose RRC paging messages if it needs to control mobiles in the state of RRC idle or RRC inactive. It delivers those messages on the paging control channel and paging channel, which maps on the PDSCH. A base station explicitly schedules most of a mobile's uplink data transmission. However, that causes a problem because the base station does not know the exact location of a mobile in the state of RRC inactive, and does not know that a mobile is in RRC idle there at all. To solve the problem, the mobile can contact the base station without any prior scheduling by using the RAG and PRAG. So the downlink control information mainly comprises scheduling commands and scheduling grants by which the base station alerts the mobile to a forthcoming downlink transmission on the PDSCH and gives it resources for an uplink transmission on the PUSCH. So there are three main types of uplink control information: the hybrid arc of the base station's transmission on the PDSCH, scheduling requests if the mobile wishes to transmit on the PUSCH but does not have the resource to do so, and feedback about the nature of the downlink radio channel, that is known as channel state information, that is a CSI. So downlink control information is delivered on the physical downlink control channel, that is PDCCH, while uplink control information is delivered on the PUSCH if the mobile is transmitting data at the same time, and on the PUCCH otherwise. Now as for the physical signals, the PSS and SSS help the mobile to acquire a new cell by transmitting information such as physical cell identity. The demodulation reference signal, DMRS, is an amplitude and phase reference that helps the receiver to demodulate the incoming signal, while the PTRS, that is physical tracking reference signal, supports that process by helping the receiver to compensate for timing jitter at higher carrier frequencies. Now, on the uplink, the sounding reference signal, that is SRS, helps the base station to estimate the best choice of uplink subcarriers as well as the best modulation scheme, coding rate, and antenna configuration. On the downlink, that role is filled by the channel state information signaling reference, that is the CSI-RS. So there is no equivalent to downlink cell specific reference signal from LTE. Instead, their role is handled by CSI-RS and DMRS. So basically whatever the channels and signals we discussed in the previous couple of slides, here we have mainly discussed all the information flow in the file here for both uplink and downlink. So this basically concludes our air interface 5G protocols. In the next videos, we will mainly discuss about the RAG and the cell acquisition. So please stay tuned. Thank you very much.